Okay, so let's address three issues that might have been bothering you. So the first is, in our whole theory, where we've established the feasibility of learning, we said it applies to any target function. We maintain this assumption that the target function is unknown kind of rigidly. Okay, but then you might have in the back of your mind that, shouldn't it be harder to learn a more complex target function than an easier target function? After all, the 3-year-old will quickly learn simple concepts, but then it takes it a lot of time to learn more complex concepts. Okay, so, where is the complexity of f? Okay, question 1. Okay. Question 2. Is it necessarily the case that the target function is deterministic? What if there are measurement errors? Is it possible that, different credit card applicants might have exactly the same application, but, one should be given credit and one should not? So could it be the case that f is non-deterministic? So, we'll address this issue of, noise or noisy target functions. Okay, and lastly, you might be wondering, well, why are we focusing on the probability of error? Is that all we care about, the probability of error? Or what should be the right way to measure error? Okay, so we'll talk about error. Now, it turns out that, none of these significantly affect the theory, but they take us closer to practice. So it's worth spending a little time on them. Okay, not much time. Okay, so first let's address the issue of the complexity of f. It didn't disappear. It's there. Even though we have assumed that, our theory holds for any target function, it's there in a subtle way. Okay, so the complexity of f. And remember that trade-off that, we have to get E in approximately equal to we need to establish that E out is approximately equal to E in for G, and E in of G is approximately equal to 0. So let's think about a complex target function. Well, a complex target function will realize in the data set as more complex data. Okay, and if the data is more complex, okay, then, you are going to need a larger hypothesis set in order to give yourself a chance at getting E in closer to 0. So more complex f will need a larger h to get E in approximately 0, just because it's more complex. And if you narrow yourself down to a few, and it turns out that few usually means simple. So if you narrow yourself to a few simple hypotheses in your target function, odds are you're not going to be able to match f even in the data. So E in won't be 0. So you'll have to choose a larger hypothesis set. Okay. But we just observed that as your hypothesis set gets larger, which becomes necessary if the target function is complex, okay, then you're going to lose control of E in versus E out. So the lasso on E out will get much more stretchy, and E out will deviate much more from E in with high probability. So with a larger h, and why larger h? Because of more complex f. So we want E in close to 0. Larger f, larger h means that, E out will deviate from E in. Okay, so while we've managed to get E in close to 0, we won't be able to conclude E out is close to E in, and therefore that E out is close to 0, because we've used a larger h. Okay, so now I'm going to come back and remind you that, these two are related by that error bar, and there are two important parameters in the error bar: the size of the hypothesis set, and one more thing, the number of data points. Okay, so one way to counteract the fact that we had to use a larger h, and remember the number of data points is in the denominator for the error bar. One way to counteract this bigger h is to increase n. Okay, so in order to get E in close to 0, no choice. We have to use a larger h. But we also have no choice. We have to maintain this theoretically. So we have no choice but to get, but to get a bigger n, i.e. more data. So let's conclude, okay, with the with perhaps what you were expecting. The target function complexity is embedded in here, but it's embedded in here directly through this trade-off, okay, and which shows that one of the, benefits of this two-step, process to learning allows us to break down exactly what's going on into the in-sample part and what's called the generalization part, the part that's controlled by the error bar. Okay, and this trade-off says that in order to learn a more complex F, you need more data. Surprise, surprise. It's harder to learn a more complex F because you need more data. So the complexity of F has not disappeared. It's there in a very natural way, and we get the very natural conclusion. We need more data to learn more complex F. Okay, now let's tackle the situation of, noisy. So noise. Again, it turns out that we don't have to really, change any of the theory. Okay, so there are two situations where noise might occur. One is that, the measurements have error. So you told me that I shouldn't assign credit to this person, but indeed I should have. So you've measured F wrong on your data. So measurement errors. Okay, and then another way in which sort of noise appears is that, you might not have all the relevant attributes needed to, let's say, approve credit. So you're missing one key attribute, and so applicants that look the same on, the attributes you measure, okay, one might deserve credit, one might not, but it's the same data point. Okay, so noise manifests as, the same data point X has a range of possible, Y values. In our case, plus or minus 1 are both possible. So plus 1 and minus 1 are both possible, and perhaps plus 1 is more likely or minus 1 is more likely. So what that means is that the target function is a distribution over the outputs. Okay. So the target function is a distribution over the outputs. And so that means that, F is really some probability distribution of the output Y given the input X. Okay, so depending on X, that determines how likely each of the different Ys are. Okay, no problem here. Okay, so take your whole input space. So for example, an example of a distribution is the target function is the target function that you will observe is F of X plus some noise. But in general, it can be an arbitrary distribution. So take your input space X, and for each input point, assign a value of F that is a realization of this distribution for that particular X. So it'll be noisy. Okay. So there'll be noisy values of F assigned to each possible value of X. No problem. That becomes a new, very irregular target function that is not a smooth deterministic function, but an irregular target function. But that's no problem because our theory works for any target function. The only thing to sort of realize here is that, the noise or the randomness in the target function will be both present in the data and also outside the data. And so that noise will affect the in-sample error, but also in an equal way affect the out-of-sample error. And that's what will sort of make sure that they are still aligned. So in-sample, because there's noise, you may not seem like you're doing well because it's not possible to model noise in-sample. And that's also the case out-of-sample. So E-in will still continue to be approximately equal to E-out. So that whole theory follows. Okay. What will change is the second step, the E-in. You won't be able to get E-in as low because of the noise. And there's no surprise. If there's noise, you're just not going to be able to model it. So your E-out will also suffer by an equal measure. Okay.